PAL.
Virtual screening of compounds from the ZINC database against PARP1 in triple-negative breast cancer. Hey everyone! Welcome back to our channel. Today, we're diving deep into the fascinating world of drug discovery, particularly focusing on a critical area, triple-negative breast cancer, or TNBC. We'll explore how researchers are using cutting-edge computational techniques to identify potential new treatments targeting a protein called PARP1, published in ChemistrySelect, 2024. So, grab your lab coats, and let's get started. First off, let's talk about what TNBC is. Triple-negative breast cancer is a particularly aggressive form of breast cancer that lacks three common receptors known to fuel most breast cancer growth. This makes it challenging to treat, as traditional therapies often target these receptors. With TNBC, the need for innovative therapies is more critical than ever. Now, what's the connection to PARP1? PARP1, or poly-A-D-pyribose, polymerase 1, plays a key role in repairing DNA. When this protein is inhibited, it can lead to the accumulation of DNA damage, particularly in cells with existing weaknesses, such as those with BRCA1 or BRCA2 mutations. This is where the concept of synthetic lethality comes into play. By targeting PARP1, researchers hope to selectively kill cancer cells while sparing normal cells. So, how do researchers identify potential PARP1 inhibitors? They begin with a massive library of compounds, over 4.59 million lead-like compounds from the ZINC database. Using a process called molecular docking, they simulate how these compounds interact with the PARP1 protein. Think of it like trying to fit different keys into a lock to see which one works best. In this study, the researchers used a specific tool called FRED, which stands for Fast Rigid Exhaustive Docking. It allows them to predict the best binding poses of the ligands, or potential drugs, with the PARP1 protein. They found 5 promising candidates, labeled Z01 through Z05, with varying binding energies. The lower the binding energy, the better the compound fits the target. Let's break down those binding energies. For instance, Z01 had a binding energy of -20.06 kcal/mol, making it the strongest candidate. It formed hydrogen bonds and pi-pi stacking interactions with key amino acids in PARP1, like his 862 and tier 896. These interactions are crucial because they help stabilize the compound within the protein's active site. But it doesn't stop there. The researchers also performed ADMET analysis, which stands for absorption, distribution, metabolism, excretion, and toxicity. This analysis helps determine if the compounds are safe and effective for use in humans. They found that none of the lead compounds violated key drug likeness rules, meaning they have good potential for development. Next up, they conducted molecular dynamics simulations over 100 nanoseconds to assess the stability of the protein-ligand complexes. This step is crucial because it mimics real-life conditions, allowing researchers to observe how the compounds behave over time. They analyzed metrics like RMSD, which tells us about the overall stability of the complex, and RMSF, which indicates how much individual residues fluctuate during the simulation. The results were promising. The compounds Z02, Z03, and Z04 showed high binding affinities and enhanced stability, with Z04 being highlighted as the most effective candidate for further testing against TNBC. The team used a method called molecular docking to evaluate how well these compounds could bind to PARP1. They identified the top 5 compounds based on their binding energy, which is a measure of how tightly a compound can attach to a target protein. The lower the binding energy, the better the compound binds. Here are the top contenders. 1. Z01 had a binding energy of -20.06 kcal/mol. 2. Z02 followed with -18.79 kcal/mol. 3. Z03 came in at -17.72 kcal/mol. 4. Z04 had -17.32 kcal/mol. 5, and finally, Z05 with -17.20 kcal/mol. The negative values indicate that these compounds have a strong affinity for PARP1, and Z01 stands out as the most promising candidate. Next, let's talk about the molecular interactions between these compounds and PARP1. Each compound forms specific interactions with amino acid residues in the protein, which are crucial for binding. For example, Z01 formed hydrogen bonds with his 862 and had pi-pi stacking interactions with tier 896 and tier 907. Z02 also showed pi-pi stacking with the same residues and had some weaker hydrogen bonds with others, like GLY876 and GLO988. These interactions are vital because they help stabilize the compound within the binding site of the protein, enhancing its potential effectiveness as a treatment. After identifying these promising compounds, the researchers conducted molecular dynamics simulations for 100 nanoseconds. This step is crucial because it allows scientists to observe how the protein-ligand complexes behave over time, providing insights into their stability. They analyzed several parameters during these simulations. 1. RMSD or root mean square deviation, which helps track how much the structure of the protein changes over time. A stable RMSD indicates that the compound remains bound to the protein without significant structural changes. 2. RMSF or root mean square fluctuation, which measures the flexibility of each amino acid in the protein. This helps identify which parts of the protein are stable and which are more dynamic during the interaction. 3. Radius of gyration, RG, which gives an idea of the compactness of the protein-ligand complex. A lower RG value typically indicates a more compact and stable structure. 4. Finally, they looked at the number of hydrogen bonds formed during the simulation. More hydrogen bonds usually mean a stronger and more stable interaction. All these analyses showed that the complexes remained stable throughout the 100 nanosecond simulation, which is a great sign for their potential as therapeutic agents. In summary, the study not only identified several lead-like compounds with strong binding affinities to PARP1 but also confirmed their stability through rigorous simulations. Among these, Z04 emerged as the most promising candidate for further experimental validation. This research showcases the power of computational methods in drug discovery. By virtually screening millions of compounds, scientists can identify potential new therapies for challenging diseases like TNBC. The findings not only pave the way for new treatments but also demonstrate the importance of understanding molecular interactions in the fight against cancer. Thanks for tuning in. If you found this video informative, don't forget to like and subscribe for more insights into the world of science and medicine. Have any questions or topics you'd like us to cover next? Drop them in the comments below. Until next time, keep exploring.
PharmaPal.